Yes, I'm audible. వినబడుతుందండి? హలో 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 నారాయణ, I'm audible. Hello, please respond.
సార్ గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్. మరి వాయిస్ ఒకసారి క్రాస్ చెక్ చేయాలి కదా. వాయిస్ వినబడుతుందా లేదా క్రాస్ చెకింగ్?
వాయిస్ అర్థం కావట్లేదు సార్.
ఇప్పుడు వినబడుతుందా?
కొంచెం సార్.
అదే ఈ సిస్టమ్ లో కొంత ప్రాబ్లమే. ఇప్పుడు ఓకే కదా?
లైట్ గా సార్, ఇంకా కొంచెం రావట్లేదు సార్ పూర్తిగా వాయిస్.
ఇప్పుడు
ఓకే సార్, ఇప్పుడు ఓకే సార్.
So tomorrow we will discuss question paper. So today some more important questions we have to learn today. Okay. Please hear. So today discuss some more questions. Define a uniformly continuous function in metric space and give an example of a function which is continuous but not uniformly continuous. See here, define a uniformly continuous function as a metric space and given an example of a function which is continuous but not uniformly continuous. This is also earlier the related problem I told you. So the definition we have to write. See here, let F be a continuous function from the metric space X into metric space Y into metric space Y. So see here, given epsilon greater than 0, there is, suppose X is always metric space on Y, so there exists a number that therefore delta greater than 0. So already we know that X comma Y belongs to X. So this is a statement I am writing now. D of X comma Y less than delta D of Y F of X comma F of Y, that is less than epsilon. So D of X comma Y less than delta, we are writing D of Y F of X comma F of Y less than epsilon, we are writing. So the F is said to be uniformly continuous on X. So therefore F is said to be uniformly and continuous on X. Then F is said to be uniformly continuous on X. See here, then proof I am taking here. We know that the function f of X is equal to X square, correct or not? F of X is equal to X square, correct or not? One function. Please respond. Hello? I am audible? వినబడుతుందా అండి? Therefore f of x is equal to x square is continuous on R. So therefore the function it is continuous on R but this function is not uniformly, continuous on our. See here, f of x is equal to x square, so it's continuous on our. But we are taking this function not continuously uniform on our. Why? Because there is a real number, but there is a number, but there be a number, there be a number delta epsilon which satisfies the condition, which satisfies the condition of uniform continuity. So the condition of uniform continuity. 1 minute only. So sorry, let x greater than 0. So therefore y is equal to x plus delta by 2. That is equal to modulus of x minus y less than delta. So we are taking here d of f of x comma f of y. We are taking here d of f of x comma f of y. So d of f of x minus, therefore we can write here x minus y and x plus y modulus of x minus y and modulus of x plus y. This showing is less than x1. So therefore we are taking here delta by 2. The simplification is 2x plus delta by 2. Why? Because it's a minus 1 plus 5 should be a 2x plus. So less than epsilon over delta by 2. So 2x plus delta by 2 less than epsilon. So it's equal to x delta plus delta square by 4. So this after the simplification, that one is x delta plus del square by 4. That is less than epsilon. Everyone is less than epsilon. So therefore x delta is less than epsilon. So therefore when x less than x delta less than epsilon, that means x greater than 0. So therefore x greater than 0 condition here, x belongs to R, or x delta belongs to x delta less than epsilon we are taking here. Y means x delta less than belongs to, in condition x greater than 0 only, that is x delta less than epsilon. This is impossible if epsilon is a fixed number, delta does not depend on x. Hence the function x square is not uniformly continuous on. And if the fixed number of delta does not depend on x, so therefore the function x square is not for uniformly continuous or those. So therefore it can be is not continuous on showing. Why? Because x greater than 0 we are showing here. The next question. If f and g are continuous real functions defined on a metric space x, then f plus g and alpha if are also continuous, where alpha is any real number. See here, if f and g are continuous and real functions given in a metric space x, then f plus g and alpha f plus g and alpha f are continuous where alpha is any real number. See here, we can prove that here. This is a statement. Now we are taking the proof here. Let x naught belongs to x, since F and G are continuous x naught. So F and G are continuous on x naught. Given epsilon greater than 0, there exists delta y greater than 0 and delta greater than 0. See here, F and G are continuous epsilon greater than 0, delta 1 greater than 0, delta 2 greater than 0, such that we are taking here d of x comma x naught less than delta 1, that is f of x minus f of x naught. So dx minus x naught less than delta 1, that is f of x minus f of x naught less than epsilon by 2, and the d of x minus x naught less than delta 2. This is delta 1 I am taking here. This is delta 2 in condition dx minus x naught. So this is taking g of x. That implies here g of x minus g of x naught less than epsilon. So see here, this is x minus x naught delta 1, that is f of x minus f of x naught less than epsilon. G of x minus x naught less than delta 2, the g of x minus x naught less than the epsilon by 2 we are taking here. So therefore, if delta is equal to what we are taking here, minimum of delta 1 and the delta 2 we are writing here. So therefore, minimum of writing here d of x comma x naught. We are writing here d of x comma x naught is d of x comma x naught. We are taking here less than delta. So therefore, we are writing here that is f of plus d of x minus f of plus g x naught. Here f of plus g of x minus f of plus g x naught. We are writing here. See here, that is less than or equal to f of x minus f of x naught plus g of x minus g of x. కలుపుతున్నా నేను f of x minus x naught, g of minus x naught. These total values is equal to less than epsilon. This is total values we are writing less than epsilon. So because we are writing here, hence we are taking here f plus g continuous. F plus g is continuous. F plus g is continuous at x naught belongs to x. So y belongs to f plus g. F plus g is continuous and x naught belongs to x, and less than epsilon ouతుంది. If alpha is equal to 0, obviously alpha is a continuous function on x. Here obviously alpha is a continuous function on x. If alpha less than 0, therefore epsilon by alpha greater than 0. So alpha less than 0, epsilon by modulus of alpha greater than 0. See here, this is the, so we can apply delta greater than 0. So therefore x minus x naught less than delta, we can find here that f of x minus, already told you both in the modulus, that is less than epsilon by alpha. Already told this is epsilon by epsilon. So f of x minus x naught less than epsilon by alpha. So therefore we can take here, we can write here then delta f of x minus delta f of x naught is equal to alpha. We are taking the common here. So therefore f of x minus f of x naught less than epsilon if x minus x naught less than delta. So therefore the alpha is continuous. So therefore alpha is continuous that x naught belongs to x. So this is the beginning true. This is the beginning true. This is a being very true here. We are taking here x naught belongs to x. We are taking here. So to follow the f plus g here, what we are taking here, alpha, f plus g and alpha are true. Why? Because it's a less than epsilon, and almost all delta f of x minus delta f of x naught to alpha common step. F of x minus x naught less than epsilon out in what f plus g and alpha f are also continuous. But where alpha is on a real number, we are writing where alpha is on a real number. So one statement of this one. Another question. Are you understanding, all of you? Another question. Define the complete metric space in the project the real number system here. define a complete metric space and prove that the real number system or is a complete here. So definition here, we can take on definition. The metric space X is called a complete metric space. So here a metric space X is called a complete metric space here. Already know that a space is every Cauchy sequence. Every Cauchy sequence in X convergence to a point in X here. Every Cauchy convergence in X convergence to point in X. So we can take the proof here to prove every Cauchy sequence. To prove every Cauchy sequence of real numbers is convergent. So to prove every Cauchy sequence of real numbers is convergent, so therefore we can take here let Sn be a Cauchy sequence. Let Sn be a Cauchy sequence of real numbers. Let Sn be a Cauchy sequence of real numbers we are taking here. So we define here the sequence nk of positive integers by induction. So see here, let's define the sequence nk of positive integers by induction as follows here. We can write here that is nk minus 1. In the smallest positive integer, that is the smallest positive integer, greater than nk. So we can take that the follows the induction as we can take that nk minus 1 to nk, right? Because nk minus 1 is the smallest positive integer greater than nk such that we are writing this one. So therefore, Sn minus Sn. So Sn minus Sn less than of 1 by 2 whole power k plus 1. That is n comma m greater than or equal to nk. So see this is equation 1. The modulus of Sn minus Sn less than 1 by 2 power k plus 1. So n comma m greater than or equal to nk. That is let ik interval. Let ik be the closure interval that is S n k minus 2 power minus k plus 2 power minus S. Please mute. Mute me. Prashant, Bhudevi mute. So let I comma ik be the closure interval. We are taking the plus and minus. That is Sn S base nk minus 2 power minus k and Snk plus 2 power minus k. And one is subtraction and one is addition. We are taking both the values here. So therefore we are taking here also ik, that is 2 into 2 power minus k. We are taking one addition multiplying that is equal to 0. So denominator was 0 only over this is therefore k stands to infinity. 2 power minus k, the denominator value should be there. So 0, it should be 0, k stands to infinity. So hence by the nested interval theorem, so hence we can write here nested interval theorem. The textbook is there. You can see nested interval theorem is there. So therefore intersection of k is equal to 1 to infinity. Ik contains here. Ik contains this is the one point here that is A belongs to what? That this is the point that 1 belongs to what? Then A belongs to Ik for all. K belongs to n such that a minus s n k less than 1 by 2 power k. A minus s n k less than 1 by 2 power k we are taking here. This is equation number 2. Already equation number 1 I told. The equation number 1 is modulus of s n minus sm less than 1 by 2 whole power k plus 1. Then my come I am greater than or equal to n k. That is equation number 1. So therefore again we are taking here for n greater than or equal to n k. We have by s n k minus Sn less than 1 by 2 power k plus 1. 1 by 2 power k, this is the third equation. Already we know that the two equations we know that. So therefore, hence for all we are taking here n greater than or equal to nk. So we have a minus Sn is equal to modulus of a minus Snk plus Snk minus Sn. So therefore, see here, ante a minus Snk plus Snk and addition a minus Sn రావడానికి we are adding minus Snk plus Snk, that is less than or equal to a minus Snk plus Snk minus Sn. We are separating this one with both the values of less than or equal to, we are separating this one here. So therefore, 1 less than or equal to 1 by 2 power k and 1 by 2 power k. So therefore, we are writing that 1 by 2 power by second and third equations of the equations, that is 1 by 2 power k minus 1. So it follows here limit n stands to infinity. Limit n stands to infinity is equal to s n is equal to 0. Why? Because less than or equal to 1 by 2 k power minus 1 కాబట్టి. So limit n stands to infinity, s n is equal to 0. So therefore, the every Cauchy sequence here, every Cauchy sequence, therefore every Cauchy sequence in R converges to point in R. So therefore, the real number system R is complete. The real number system R is complete. We are taking here. Clear any doubts? Clear any doubts? No one responding. Okay. Second question, another question. E subset of k subset of x. If E is finite and k is compact, then prove that E has a limit point. E has a limit point. E has a limit point in k. See here, E subset of k subset of x. E is infinite and k is compact. Then prove that E has a limit point on k. So see here, you can take that one proof here. Suppose E has no limit point on k, no limit point on k. We are taking here E has no limit point on k. So therefore, then for x belongs to k, we can find an open sphere. We can find an open sphere S of x, or the SRX S of x, which does not contain a point, which does not contain the point of E other than x. See here, which does not contain a point E other than x we are taking here. So what is the contain of the other point we are taking? Thus S of x does not contain more than one point on it. So therefore S of x does not contain more than one point. More than one point. See here, it does not contain more than one point of E. So all such here, S of x belongs to k, form on open cover. S of x belongs to k from an open cover of k. So x belongs to k is an open cover, we know that. So K is K, and since K is we are taking here compact. So the open cover K, so therefore K is compact here. So therefore we can find here. We can find here x1, x2, and so on xn in K, such that we are writing here K subset of S of x1 union of S of x2 union of S of x3 union of S of xn. So this S of xn has at most one point of E, therefore E cannot be infinite. Why? Because E subset of Sx1 and Sx2 is the union part, so it contradicts of the hypothesis. మనం ఏదైతే అనుకుంటామో అది కాంట్రడిక్ట్ అవుతుంది కాబట్టి సో అవర్ సపోజిషన్ ఇస్ రాంగ్. సో అంటే ఈ అనేది లిమిట్ పాయింట్ అని కేనే అవుతుంది. ఎందుకు సబ్సెట్ ఆఫ్ కి యూనియన్ కి మధ్యన వాల్యూస్ సాటిస్ఫై అవుతున్నాయి కాబట్టి మనకి హైపోథిసిస్ కాంట్రడిక్ట్ అవుతుంది. మన సపోజిషన్ రాంగ్ అవుతుంది కాబట్టి సో therefore E as a limit point of E as a limit point on K. So third another question, define an open cover, define an open cover, finite subcover in the compact metric space. The compact metric space give at least two examples. Of it. Say define a open cover, finite subcover in the compact metric space, and give at least two examples of it. We have learned to here. Just 10 minutes. నారాయణ గారు అర్థమవుతుందా? So therefore, we can take here this one of examples of it we can take here. So therefore, the open, what is the, anyone tell me what is the definition of open cover, anyone? What is the open cover? What is the open cover? Let X be a metric space. A subset of X and I be a set of indices. And I be a set of indices if G alpha belongs to I. See here, set of indices G alpha belongs to I is a collection of open sets. Is a collection of open sets. Here G alpha belongs to I. So it's a collection of open sets, X is such that so a subset of union of alpha belongs to I. Here it is a union of alpha belongs to I. You can take here G alpha belongs to Y. So G alpha belongs to Y is called as an open cover of A. So we denote that the open cover by open, we denote the open cover, you can write here open cover by, that is you can write G alpha. So there is open cover by G alpha, we can write here. Then finite subcover. What is the finite subcover? Finite subcover. So A subset of union of I belongs to I to N. So this is G alpha I for finite number of indices, for finite number of indices indices for finite number of indices we are taking here alpha 1, alpha 2, alpha 3, and so on, alpha n. Again we are taking here I, we are taking here then G alpha, I is equal to 1, 2, 3, and so on, n we are taking. This is called finite subcover. So G alpha is equal to I is equal to 1, 2, 3, n. So A are subset meaning of alpha I belongs to I to n. This is called the finite subcover of the given open cover alpha, that is G alpha. This is called as finite subcover. These are definitions may be asked in examinations. Then compact metric space. So see the compact metric space here. If every open cover we are taking here, of a metric space, the metric space X contains finite subcover, we are taking here. So that contains finite subcover means a subset of union of I belongs to I, G alpha for finite subindex we are taking. G alpha is open cover, we can take that the finite subcover. So therefore then X is called as compact metric space we are telling here, this one. So one example, this one. So therefore a finite point set is compact. The second one, closed interval A comma B is a compact set in R. Closed interval A comma B is a compact set in R. The two examples of this one for the differences. Another question. If X is a non-empty set and B is the standard discrete metric, then to that any subset Y is compact if and only if it is finite. X is a non-empty set and B is the standard discrete metric, then to that subset of Y is compact if and only if it is finite. So see here the proof of the this statement I am taking here. We know that every finite set is a compact or not? Every finite set is compact or not? Every finite set is compact or not? Every finite set is a compact. I am audible, all of you? Hello? I am audible అండి? వినబడుతుందా? You know that every finite set is compact, and conversely we are taking here. If Y is compact, then for each X belongs to Y, we are taking here. If Y is compact, then each X belongs to Y, therefore exists, therefore epsilon there is 0, that is S epsilon X, that is equal to X. So therefore X is open. So if S epsilon X is X raster, therefore the condition is X is open here. So therefore if we consider here, therefore conversely here also we consider the set of all such S epsilon X for various X belongs to the here. So then that is an open cover. Then that is on open cover. We are taking the interval of y and being compact and being they are taking here and being y compact here. So it has a finite subcover. So therefore y consists of it has a finite subcover where when is the by y being is a compact here. So y is consistent of finite number of points here. Y is a consistent number of points here. So therefore we can finite set is a compact. Conversely and truly also this is compact here. The question. E subset of x. Then E is connected relative to x if and only E is connected so E subset of x and then E is connected to relative to x if and only if E is connected relative to E we are taking here. So if E is not connected, we are taking every finite set is compact and converts to this one. మనం ఇక్కడ ఏం చేస్తున్నామంటే here E is not connected. E is not connected to relative to x. Is not connected relative to x. There exists non-empty disjoint open set. There exists non-empty disjoint open set. And B here we are taking here non-empty open. What is the disjoint open set? Anyone tell me? Non-empty disjoint open set. Non-empty disjoint open set. Hello? వింటున్నారా అండి?
నాకు మీ వాయిస్ బ్రేక్ అవుతుంది సార్.
మీరు అడగలేదు నేను ఇన్నిసార్లు చెప్తున్నాను అది ఇప్పుడు ఓకేనా?
మామూలు చూస్తున్నా మీ వాయిస్ బ్రేక్ అవుతుంది సార్.
ఇప్పుడు నారాయణ గారు ఇప్పుడు ఓకేనా?
సార్
ఇప్పుడు ఓకేనా?
కొంచెం సార్ లైట్ గా.
సరే ఈ ఆఫీస్ సిస్టమ్ ఇట్లా ఉన్నట్టుంది. ఇఫ్ నాన్
సిగ్నల్ ప్రాబ్లం అనుకుంటా సార్.
ఇది వైఫై అండి. If disjoint open set A and B, open set and A and B such that we are taking here. I am writing కదా, writing కనబడుతుంది కదా. If A intersection not equal to 5, B intersection not equal to 5, subset of A union B, and we are taking a intersection of A intersection of B. What is that value? What is that value? Is 5. We have intersection of that is 5. So therefore, A dash is equal to A intersection of B. B dash is equal to B intersection E. Then A dash. Therefore, we are writing A dash. A dash and B dash are non-empty subsets. Therefore, A dash and B dash are non-empty subsets. Open relative to E. Open relative to E such that we are taking here A dash intersection E is equal to 5. B dash intersection B is equal to 5. So B subset of A dash union of B dash. A dash union of B dash. See here, A dash intersection E is equal to 5. B dash intersection is equal to 5. B subset of A dash union of B dash. So therefore, E intersection of A dash intersection B dash also is equal to 5. Intersection anna subset anna రెండు ఫైల్ అవుతున్నాయి కాబట్టి intersection of A dash intersection B dash is equal to 5. So therefore, E is not connected to B equal to E we are taking here. So therefore, E is not connected related to Next question. This is the first part, then we are taking conversely here. Suppose E is not connected related to E. Suppose E is not connected related to E. Then the exist non-empty sets G and H. Existing non-empty sets G and H we are taking here. Open relative to E. You can take that G intersection E is equal to 5. So G intersection H intersection E is equal to 5. So E subset of G in H and the E intersection G intersection B. E intersection B, already I told this one, E subset of G union A, that is E intersection of G intersection B is equal to 5. So therefore we are taking here E is equal to G union of H we are taking here. So G and H are G union H of the G and H are open here relative to E. Relative to E we are taking here where exists G1 and E H1 is open. H1 is open in X such that so G is equal to G1 intersection E not equal to 5 and H1 intersection E not equal to 5. So therefore G1 intersection E not equal to 5, H1 intersection not equal to 5. But even the E subset of G1 union of H1, so E intersection of G1 intersection H1, so this is equal to the condition is the same here. So therefore E is not connected to relative X. We are taking the generally not related to X, not related to X. So G intersection G1 intersection G1 intersection H1 not equal to 5 out of property is not related to X. Why? Because E is not connected. So E is not connected related to X here. Then another question, through the continuous image. Through the continuous image of a compact space is compact. Through the continuous image of a compact space is compact. So see here, also in question they will ask f x times y is a continuous function on a compact metric space, then f of x is compact in y. అది కూడా ఇమేజ్ అయిన అడగొచ్చు కంటిన్యూస్ ఫంక్షన్ ఆఫ్ ది కంపాక్ట్ మెట్రిక్ స్పేస్ ఈ f of x is in compact y అని కూడా they will ask in the examination. So we can take here prove that f of x is a compact subset. F of x is a compact subset of y. F of x is a compact subset of y. Consider an open cover. Consider an open cover that is G alpha belongs to I. So that is G alpha belongs to I. Know that this is of f of x. This is of f of x we are taking here. This is f of x of we are taking here. So therefore, since G alpha is an open wave, since G alpha is open in y, and f is continuous function, and f is continuous function. F is continuous function we are taking here. So therefore, f inverse of G alpha is open in X. Already I told in the earlier class, f inverse G alpha is open on X. You can observe that X is equal to union of alpha belongs to Y, f inverse of G alpha. F inverse of G alpha we are taking it. So therefore, since X is compact here, since X is compact here, there exists a finite number of indicates here, alpha 1, alpha 2, and so on, alpha n, such that X is subset of f inverse of G alpha 1 union of F inverse of G alpha 1, union of F inverse of G alpha 2, and union of F inverse of G alpha n we are taking here. So observing that here x belongs to x implies here x belongs to F inverse G of alpha I we are taking here. For some we are taking here I we find that f of x belongs to G alpha I, f of x belongs to G alpha I. So for some in 1 less than or equal to I less than or equal to G alpha for some I less than or 1 less than or equal to I less than or equal to n. So therefore, just a minute. So 1 less than or equal to 1 less than or equal to I less than or equal to n we are taking here. So therefore 1 less than or equal to I less than or equal to n. So therefore f of x belongs to G alpha I we are taking here. So that is the first sum 1 less than or equal to I less than or equal to n. So therefore f of x subset of G alpha I union of G alpha 1 G f of x is then G alpha 1 G alpha 2 union of G alpha n. G alpha 1 union G alpha 2 union G alpha n. So therefore f of x is compact for the subset of all the unions of the subset here. So therefore f of x is compact here. Another question. Suppose f1, f2 and f of k are real functions on metric space x and it stands to Rk is defined. F bar x stands to R power k is defined by f of x is equal to f1x, f2x, and the of k of x we are taking here, that is x belongs to f1x, f2x, and f of k belongs to x belongs to. So then prove that f of f bar is continuous at x if and only if f1, f2, and f of k are continuous at x. Here, to prove that f is continuous at x, if and only f1, f2, fn, so on f of k are continuous at x. So therefore we are taking that this one. Let x comma y belongs to x in modulus of f bar x, in modulus of f bar y, summation of y is equal to 1 to k, that is f of ix minus f of y square whole power 1 by 2. See here, f of ix minus f of I y square whole power 1 by 2. So this is the we have here f of 1 of x, f of I of x is here minus f of I of y we are taking here. Then we are taking less than or equal to then f bar x minus f bar y we are taking here. So what is the condition f of 1 f of ix minus f of y less than or equal to f bar x f bar y for what? For I is equal to 1, 2, 3 and so on k we are taking here. for each f of I is continuous, f of I is continuous, x belongs to x, given x1 greater than 0, therefore exists delta 1 greater than 0 such that we can take here modulus of x minus y less than delta 1, that is f1 x minus f5 x, sorry, f5 x, f5 x and f5 y, f5 x minus f5 y, that is epsilon by root k. So here, modulus of x minus y less than delta 1, that is f5 x minus f of y less than, that is epsilon by root k we are taking here. So therefore, delta is equal to minimum of delta 1, delta 2 and delta k. So modulus of x minus y we are taking a less than delta. Suppose the we are taking a bar f of x bar minus f of y bar, it is less than epsilon. Therefore f bar is continuous. Therefore f bar is continuous. X, when given epsilon greater than 0, there exists delta greater than 0. Such that, so therefore, epsilon greater than 0, we are writing here, the condition is satisfied and delta greater than 0. So therefore, we can write here this one, modulus of x minus y less than delta, that is summation of I to k, modulus of f of ix minus f of y. This is whole square and whole power 1 by 20. End cancel about it, therefore f of ix minus f of x. But we are taking here this one, f of ix minus f of I by, so that is less than epsilon. Already we told you this is 1 less than or equal to I less than or equal to k. So 1 less than or equal to I less than or equal to k. So therefore f of I is continuous on x. So therefore f of x is I continuous. So therefore f of I is continuous on x we are taking here. So therefore I for I is equal to 1, 2, 3 and so on to here. The next one, if f bar is equal to f1, f bar and g bar, if f bar and g bar are continuous mappings, of the matrix spaces of the matrix spaces into R power k, then the bar plus g bar and the f dot g dot multiplication are continuous on this. Are continuous on x we are taking here. So therefore, proof we are taking here, if f bar f1 comma f2 f of k, g bar is equal to f bar, g bar is equal to g2 and gk. The bar comma g bar are continuous. The bar comma g bar are continuous if and only we are taking here. F5 and GA are continuous. So F5 and GA are continuous. F and GA are continuous here. F and GA are continuous, but the condition is 1 less than or equal to y less than or equal to k. That is it. So since F and GA are, we know that they are real functions. Since F and GA are, since F5 and GI are real functions. Since F5 and GI are real functions, and since some product of since since f and j are real functions, f and j are the real functions here and the continuous here, and the fi bar plus j bar and fi bar and the therefore r and comma gi are continuous functions. So we write here bar plus g bar f1 plus g1 f2 plus g2 and so on. Here it is f of g2. So we are taking the f1 plus g1 1 2 3 4 and we are taking up to k gk. Then f dot g f bar into g bar is the summation of I is equal to 1 to k plus 5 here. I think it follows that here. F bar plus g bar and f bar g bar is continuous. Why? Because continuous here. So f bar and g bar is f bar equal to f1, f2, f3 and fk. G bar equal to g1, g2, gk. Then f bar, g bar are the continuous. If and only continuous is 1 less than or equal to continuous. So therefore the less than or equal to k. So that's why. So that's the real continuous function. So therefore f bar plus g bar and f bar, g bar is continuous, and addition and the multiplication is one. And the problem of the one we have to see here. All of you listening? So b bar f plus g b alpha less than or equal to integration of a to b bar plus b alpha a to b bar b alpha. F b f plus g. Already I told you this is f plus g alpha, f d alpha, g d alpha. Already told in the last classes. So see here, state and prove Fulani theorem. Now I am going to that one. Already this problem I told in the previous classes. State and prove. Fulani. Fulani theorem R it out advochu, let f belongs to R. A comma b closed interval. So therefore for each we are taking here b greater than a greater than 0. Whichever advochu, other advochu. So the b greater than 0, the conditions first for a greater than 0 and the conditions is that a then first condition is taken to low, limit extends to infinity, integration of 1 to x f of t dt exists and is equal to b. Second one, limit extends to 0 plus x by b ఇస్తున్నాము. ఇది ఫంక్షన్ ఇది కొంచెం ప్రూవ్ చేయడం f of t square by dt exists and is equal to a. Then for each a greater than 0 to infinity f of ax minus f of dx by x exists and equal to exist to equal to b minus a in a by b. This is the conditions you have to write. Where f belongs to a, b for each a greater than 0 and step for either istaru taken to Friendly theorem ante you have to write all these conditions and prove that immediately. Then we are going to without losing of generality, we may assume that without generality b greater than a greater than 0 is approved. First we shall consider here integration of 1 to infinity f of ax minus f of dx by x dx. Let p greater than 1. We take here f of x minus f of dx by x. Let's keep it and one. Then we have to take here I is equal to integration of 1 to t f of ax minus f of dx by x. So f of a already after the Rasan n into dx. So simplify integration of 1 to t f of ax by x into dx minus f of dx by x into dx. Again, you have to take integration of 1 to t. You have to take 1 to t of t. So again, I am taking the simplification of this equation here. Integration of a at f of t అంటే ఏని కామన్ తీసుకున్నాను బయటికి f of t by t dt ఇక్కడ కూడా అంటే ఇంటిగ్రేషన్ ఆఫ్ b to bt f of t by t dt dt అంటే this is equation number 2 అంటే నేను అక్కడ దీన్ని బయట ఏని bని బయట తీసుకొని రాస్తున్నాను by substituting here t is equal to a by t is equal to ax in the first integral and the t is equal to dx in the second integral we are taking here. Now I is equal to integration of a to b f of t by dt minus integration of into a to bt. A to b ఒకటి తీసుకున్నాను a to bt ఒకటి తీసుకున్నాను ఇక్కడ రెండు సెపరేట్ చేసి తీసుకుంటున్నాను రెండు సెపరేట్ చేసి తీసుకున్న f of t by dt వీటిలే కానీ ఇంటిగ్రేషన్ ఆఫ్ a to at ఇది a to integration of t is equal to ax plus రాస్తున్నప్పుడు integration I is equal to తీసుకుంటాం integration of a to b f of t by t dt minus integration of at to bt f of t by dt తీసుకుంటాం we write here integration of 1 to x f of t dt this is equal to x into g f of t dt is equal to x into g of x. It implies that g of x stands to b, that is x stands to infinity. G of x stands to b, x stands to infinity. Using integration by part system we are doing here. Integration by part system and second integral you can obtain here, you can write here. So integration by parts, you know that. Then above the second integral we are taking here. Yeah, here we write here. Integration of 1 of y f of t by t dt dt is equal to integration of 1 of y 1 by t d t gt. See here 1 by t d d dt we are writing here y g of y by g by y g by y minus 1 into g by y. After simplification writing y into g by y and 1 into g by y and second simplification we are writing the minus here again here 1 into y t g integration by parts I am taking here t g t into d into 1 by t. This is a part of this one. So therefore we are taking the simplification of this one and the numerical part y by y is against g y minus g y minus g y into 1 g y. So plus integration of 1 to y g t by t into dt we are taking here. So g1 in front of the system taking here 1. So putting on y is equal to dt, putting on y is equal to dt and y is equal to at. Putting on y is equal to at and the y is equal to dt respectively and the subtracting here. So therefore integration of at integration of at to dt f of t by t dt g of dt minus g of t. See here g of dt minus g of at plus integration of at to dt that is gt by t. ఇంతకుముందు అనే ఈక్వేషన్ రాస్తున్నాను again బట్ సబ్స్ట్రాక్టింగ్ చేయాలి కాబట్టి మళ్ళీ రాస్తున్నాను సబ్స్ట్రాక్టింగ్ చేస్తే ఏమవుతుంది అనేది చూపించే ప్రయత్నం చేద్దాం. సో since g is continuous and reciprocal function reciprocal function 1 by t we are taking here is positive. Just a minute. So continuous and the reciprocal function, continuous and reciprocal function 1 by a 1 by t is positive here. So 1 by t is a positive here. So therefore the valued in we are taking here, valued in at comma bt we are taking here, at comma bt. So we can use the mean value theorem of Riemann integral. You know the Riemann integral theorem, you know that, and they conclude the series here in the series in the closed interval at comma bt. So therefore, integration of at to bt we are writing here g of t by t dt. We are taking here g of x integration of at to dt dt by t. So it is g of x from g by t తీసుకొస్తున్నాం మనం. సో అప్పుడు తీసుకొస్తే dt by t అవుతుంది. సో dt by t అవుతుంది. So therefore అప్పుడు ఏమైతుందంటే g of x equal integration means integration of b by a. This is g of x we can write that it's integration of b by a. Substituting this equation is equation number 3. What is equation number 3? So integration of at to bt f of t by dt dt. So dt is equal to g of t minus g of at plus integration of at dt by dt by t into dt. This equation we are substituting in the screen. You are seeing here this formula. So substituting in 3 and the corresponding expression, the second expression also, you can get here these values here. So therefore, I is equal to integration of a to b f of t by t into dt minus g of dt plus g of at minus ఇంతకుముందు వచ్చింది g of x in b by a. So these are all the values that I am substituting here. So we substituting we get here I is equal to a to b f of t by t into dt minus g dt plus g of at minus g of x in b by a. See here, integration of a to b f of t by dt. I'm substituting here the same value in the x is number in at minus dt. Now we're taking the limit 3 stands to infinity so that x also approach alpha. So x approaches alpha, so we get here integration of a to infinity. Integration of a to infinity here. F of ax minus f of dx by x dx equals integration of a to b f of t by t dt minus b. Already I told that b by a, b in b by a, we are taking here the formula integration, that is integration of a to b f of t by t into dt we are taking here. So therefore plus b in b by a, already I told here this is fourth equation. I am substituting the values here and sum number 80 minus 80 comma bt. Now taking limit 3 times to x with alpha, we get here see here that's the b minus a 4. So shall note that here. Shall we note that here? Shall now take zero less than s less than 1, and we write here j is equal to j of s integration of s to 1 f of a of x minus f of b of x by x into b. So this is the substituting value here, that is b is equal to 1 by s, and f of y is equal to, we are writing that f of y is equal to small f of 1 by y, and the above we are taking at j is equal to integration of 1 to t. So therefore, f of y by a and the values in the simplified on f of y by b by e into dy. So therefore, 1 by x integration of 1 to x f of t dt. 1 by x we are writing the integration of x to 1, that is f of t t square. So therefore f of t t square, that is stands to 0. So that 1 by x stands to 0 means x stands to infinity. So we obtain from the hypothesis of the second one here. So therefore we can write here 1 by x 1 to x f of t dt. So as we and x stands to infinity, we are taking the f of t dt stands to x stands to infinity. So that's why we can use the first part with the can use the first part with f comma 1 by a comma 1 by b. In the place of 1 by a comma 1 by b, we can place here f of a comma f of f a comma b comma a comma b. We obtain here only. So therefore, we are writing here integration of 0 to 1 f of ax minus f of 3x by x is dx. Simplification, limit s tends to 0, that is plus, that is j of s. Already I told that limit we are taking here t tends to infinity, that is 1 to t, that is f of y by a and y by b, f of y by a minus y by b by b. We are taking b function, so that's what we are taking here. So therefore, integration of 1 by a to 1 by b, f of t by t into dt minus a in by b తీసుకున్నాను ఇక్కడ a తీసుకున్నాం that 1 by b by 1 by a. So therefore integration of 1 by a and 1 by b. So f of t by t dt equal to minus integration of a to b f of x by x dx. We are taking here these conditions of put t is equal to, we are taking here 1 by x here. So put we are taking integration of 0 to 1, we are taking here integration of 0 to 1, we are taking here f of dx minus f of dx by x. So therefore into dx we are taking the minus is the common part here, minus d into df of t by t into dt minus a. This is the fifth equation. But 4 and 5 completes here the proof of this one. So a by b and f of minus lo place lo positive negative positive వస్తున్నాయి కాబట్టి this is a complete proof of this. Just a minute. The most important thing also ask me. So see here, and another problem we have to discuss. Do that. This series of L function define having derivatives, define function having derivatives all orders. So 1 minute only, please. One, 2 minutes, wait. So the real function defined having a derivative, all orders in R we are taking here. So with the convergence uniformly, with which convergence here, uniformly in R, some function which has never which has never we are taking here. Uniformly or some or uniformly on R to some of function which is never which is now here as a variable. So the proof we are taking here for n greater than or equal to 0, the of n of x that is we are taking 3 by 4 whole power n formula sine square of pi square pi by 24 power mx. So each f of n is finitely we are taking here differentiable at all points of R. F of n is finitely differentiable at all points of R, and since f of n less than or equal to the condition 3 by m whole n, it follows that there is a Weierstrass n-stat test summation of n is equal to 0 to infinity. N is equal to infinity. F of n of x is convergence uniformly or not uniformly on R we are taking there. So let we have to denote here here the sum of some function let f be the some function here is f is continuous in R. We shall prove that f dash alpha does not exist for any a belongs to R. For any a belongs to R, fix a belongs to R less than alpha n and the sequence of alpha n, sequence of beta n, the alpha n equal 4 power minus n and 4 power n into e. So then beta n, so 4 power minus n, 4 power n into a plus 1 for n greater than or equal to 0. So alpha n less than or equal to a, alpha equal to beta n we are taking here. For alpha n stands to alpha, beta n stands to also a. So here alpha n stands to a and beta n stands to also a here. So therefore n stands to infinity. Fix here. So fix here m belongs to z here. So observe that here 4 power m bm minus alpha m we are taking here is equal to 1. Therefore 4 power m b power m is an integer. So therefore f of m beta m, f of m beta m, f of m alpha m, f of m beta m, f of m alpha m. So we are taking here 3 by 4 whole power m we are taking here. So therefore n greater than m is taking here 4 power n beta m minus alpha m we are taking here as an integer. F of n beta m is equal to f of n alpha m. So f of n beta m and alpha m and both the values are same here what we have taken here. So consequently we have here the f of beta n minus f of alpha m. So the summation of n is equal to 0 to m. Summation of n is equal to 0 to m. So therefore f of m beta m minus f of m. So we are taking here 0. No reason here 4 power n alpha n here and 4 power n beta m also. So that we write here sin square pi by 2 4 power n beta m minus sin square pi by 2 4 power n alpha m. This is the values of we are writing here. So 1 by 2 cos 4 power n alpha m pi minus cos 4 power n beta m pi. అంటే ఆ కండిషన్స్ అక్కడ రాసేస్తున్నాను నేను. That is less than or equal to sin 4 power m beta m minus common తీసుకున్నాను 4 power n ని. So therefore that is 5 by 2 less than or equal to 4 power n minus m into 5 by 2. This is the taken common in the values of this one we are taking here 1. So see here modulus of bn minus f of alpha n we are taking here that is less than or equal to 3 by 4 whole power 3 by 4 whole power m minus 5 by 2 summation of n is equal to 0 to n minus 1. That is 3 by 4 n 4 into n power minus 1. So that is 4 power minus and I am taking the common here 3 power m minus 5 by 2. The summation of n minus 1 n is equal to 0 to 3 power n we are taking here. So 4 power minus m I am taking here 3 power m minus 5 by 4 3 power m minus 1. The simplification I am doing here is not equal to 3 by 4 whole power m minus 1 minus other simplification of the this being a true for all m greater than 0. It follows that here f of beta m minus f of alpha m by beta m minus alpha power